Hugh Woodin will continue with the second part of the story.
Okay, so we'll see whether I have accurately estimated the length and just how many misprints there are. I'm worried I'm headed toward a new definition of a wooden cardinal, the number of misprints in my slides. Okay, so if one can prove this conjecture, that if delta is an extendable cardinal, then there's a weak extender model for delta supercompact, which is contained in Hod, then one verifies the Hod conjecture, which has a lot of metamathematical consequences and arguably predicts or is a precursor to an ultimate version of L. So what I'll be doing today is, and the next two lectures, is a sequence of results constraining how one might prove this conjecture. All right, so if you take Kunin's analysis and construction of LMU, where mu is a normal kappa complete measure on kappa, then his construction gives this theorem. Delta is a measurable cardinal, then there's a weak extender model n for delta is measurable such that n is contained in Hod. And you define a weak extender model for measurable just like I did for supercompact. You can define weak extender models for any large cardinal hypothesis which is formulated in terms of extenders. And you just require that the extenders of the model come from extenders of V, or the measures. I guess I haven't defined extenders yet. So one just needs to generalize Kunin's construction of LU to the level of supercompact cardinals. And we're done. Okay, so notation for extenders. If E is an extender, remember that gave us an ultra power embedding from V into ME that enabled you to recover the extender. I'll be using this notation a lot, so hopefully we'll get used to it. Kappa E is always the critical point of the associated embedding. It's the critical point of the extender. It's the completeness of the measures or the ultrafilters in the extender. Remember, an extender is just a directed family of ultrafilters. Kappa star E will be very important. That's the image of the critical point under the extender ultrapower embedding. Now more technically, nu E is the soup of a bunch of ordinals. These are called, these are called generators. So we're looking at an ordinal psi such that psi cannot be generated by taking a function, applying the embedding J to it, and evaluating it at a finite subset of psi. Okay, those are called generators, and this is the strict soup of generators, sometimes called the natural length of an extender. If the extender was just a measure on kappa, then nu sub E would have only one ordinal in it. There'd only be one generator, the critical point of the embedding. Another really important ordinal associated to extenders is the strength, denoted rho of E, and it's just the soup of the V alphas which are contained in the ultrapower. One last important parameter associated to an extender, the space of an extender. It's the supremum of the ordinals which are sent to something below a generator, less than or equal to a generator. Okay, if you just unpack. All right, so trivial observation, the space of an extender is always a cardinal, and the strength of an extender is always at least the critical point plus 1. Now, for much of what I'll be doing today, the space of the extender will always be the critical point, but, well, no, that's actually not true, but that's the classical theory, so to speak. Okay, I want to go near the ceiling. An extender is omega huge if its strength is greater than or equal to the first non-trivial fixed point of the associated embedding. That's just about how strong an extender can be. That's the maximum possible strength by Kunin. Okay, another formulation of Kunin's theorem. It's not hard to see that the fixed point, the first fixed point of any elementary embedding from V into M, you take the critical point and take its image, and then take the image of the image and take the soup. Okay, so that's the maximum possible strength of an extender. I don't know why I'm pointing this here when I should be pointing it here. All right, so now I'm going to introduce you to a notion that I'm not going to use in the lectures, but that will be used in the notes. And the reason is it's a very important background concept to intermodal theory, and it enables me to precisely state the iteration hypothesis that I will need. So I'm just going to be giving a bunch of definitions right now, and I'll try to motivate them. It concerns iteration trees and iteration hypotheses. Now, Martin Zeeman will presumably be making similar definitions, so probably slightly different. So a coarse premouse, as opposed to a fine structural premouse, is just a pair, m delta, where m is transitive, delta is an m. We'll make m a model of Zermelo set theory with the axiom of choice plus sigma 2 replacement. If that bothers you, make it ZFC. In which case you can ignore 2. And then delta is strongly inaccessible in M. So I'm really going to be interested in M delta, but I want a little bit more above, just to make the definitions work out. So this is a central definition in set theory now. It's really due to Steele, though I'm going to give a generalized version of the definition. Okay, suppose we have a coarse premouse. An iteration tree on that is a tree order with 0. It's a suborder of the standard order. It has a length. The iteration tree has a length eta. The tree order is a suborder of the standard order on eta with minimum element 0. The iteration tree is a sequence indexed by the ordinals less than alpha of models, extenders, and embeddings. Okay, and now what I'm going to do is tell you what all these are. Okay, M0 is just the initial model, and we require that M alpha be transitive for all alpha less than eta. J gamma alpha is an elementary embedding from M gamma to M alpha. So this is an elementary sequence of models. It's just a linear, it's a sequence of models with elementary embeddings between them. And now I have to specify how you get those. So suppose alpha plus 1 is less than eta, that's the length of the iteration tree. Then alpha plus 1 has an immediate predecessor in the tree order. We always denote that alpha star. Put a subscript t if there's some ambiguity present. E alpha has to be in J0 alpha of M intersect delta. Remember, that's that initial segment of M. That's a nice ZFC model. M alpha has to think E alpha is an extender which is not omega huge. So it doesn't have the maximum possible closure strength. Okay, now this is the technical bit, but it's absolutely essential. If alpha star is less than alpha, then the space of the associated extender E alpha, which is calculated in M alpha, remember that's a cardinal, plus 1, has to be less than or equal to the minimum strength of all the extenders with index greater than or equal to alpha star and less than alpha. Why do we do this? This guarantees that E alpha is an M alpha extender. There's enough agreement between all these models so that E alpha is an M alpha star extender. So I can take the ultra power. Now I may not get something that's well-founded, but remember all the models have to be well-founded, so this has to be a well-founded ultra power. The extender is not necessarily in the model. I'm taking the ultra power of. So M alpha plus 1 is the ultra power, and J alpha star alpha plus 1 is the associated embedding. At limit stages, the tree predecessors have to be cofinal in the ordinal, and M beta is just the direct limit of the M alphas for alpha tree less than beta under the associated embeddings. So that's all an iteration tree is.
Is there a reason why you didn't addition 3A?
Yeah.
Put M alpha there, the alpha plus M alpha?
Well, J0, because it's an initial segment of M alpha. I'm keeping in the part of the model where the inaccessible is, that's all.
So it's M alpha.
Yeah, it's M
V
alpha.
is
Yeah. So here's what's going on. You start with your model, M. Now you take an extender in the model and you take an ultra power. Okay, that's what we would do in the usual theory. And we might get a model M1. Now you choose an extender here. So this is by the first extender. Now you choose an extender here. But there may be enough agreement so that you could that this extender here is actually an M extender. So you could apply that extender here if you wanted, or you could apply it here, and so forth. So at every stage you're in some model. There are all these other models. You take an extender here, and there may be many other models that you can apply it to. And you're allowed to apply it to any one for which it makes sense, subject to this requirement. And so what you're generating is a tree of models. And then the whole problem, of course, is what do you do at a limit stage? Well, you have to choose a cofinal branch through the tree. Maybe there is no cofinal branch. Or maybe, so first there must be a cofinal branch, or the tree cannot continue. But then when you choose that cofinal branch, the limit may not be well founded. So you have, at limit stages, you have to choose a cofinal branch through the tree of models such that the direct limit along that branch is well founded. Okay, so that's all an iteration tree is. In the classical theory, say Kunin's theory, all iterations are linear. So an iteration tree is a generalization of a linear iteration. And it's absolutely essential in the theory. And it's because of that it's a tree that the notion of iterability becomes complicated. Okay. I'm not going to be doing anything with this notion in the lectures, but it is in the notes. All right. Okay, so now I need to make a definition. We have our coarse premouse, an iteration tree on it, and we have an ordinal theta. Then the iteration tree is a plus theta iteration tree if for all alpha plus 1 less than eta, if I soup the spaces of the extenders E beta, for which beta star is less than or equal to alpha is less than beta, and then add theta to it, I'm less than the strength of rho alpha. And that strength, of course, is calculated in the model M alpha. And here again, beta star is the tree predecessor of beta plus 1. Okay, now that soup may be empty. Okay, if beta star is less than or equal to alpha is less than beta, then the space of E alpha plus 1 has to be less than or equal to the strength of E alpha. That was that condition. Okay, so every iteration tree is a plus 0 iteration tree. And every finite iteration tree is a plus 1 iteration tree. Okay, now, again, I'm going to very quickly focus on a special class of iteration trees for which it's only plus 1 that I'm going to be interested in. And I guess I should have said in the definition of the iteration tree, this is a bit stronger than you need. You don't need this much to guarantee that E alpha is an M alpha star extender. This is requiring much more agreement between the models than is necessary. But again, when we narrow down to the iteration trees of interest, all the variations that you would use there are equivalent. Okay, so the thing to keep in mind is it looks like that. Okay, so that's a plus theta iteration tree. Now we have to talk about iteration strategies. If you have a coarse premouse, an iteration strategy of order omega 1 plus 1 for M delta is a function I that does the following. Suppose T is an iteration tree on the initial model of length such that the length of the tree is less than or equal to omega 1, then T is in the domain of the function, and the function I at T gives you a maximal well-founded branch of limit length. Remember, it's a tree of models, so the function always has to give maximal branches that are well-founded. Okay? So in particular, that has to be a maximal well-founded branch. If you follow what the iteration tree is telling you to do at limit stages, so if you have an iteration tree on the model of limit length, less than or equal to omega 1, and that for all limit eta less than the length of the tree, the iteration strategy at the iteration tree restricted to eta is the branch the tree picks. In other words, at limit stages, the branch that the tree is picking agrees with what the function is saying you should pick. Then I of t is a cofinal well-founded branch. Okay? So basically you can think of it as if you want to iterate m delta and you're not quite sure what to do at limit stages, you're nervous which branch you're going to pick. You might get into trouble. So you consult the oracle I and it hands you a branch. And that branch is well-founded. And then you can just keep going however you want, choosing whatever extender subject to the rules of the tree. Then you get to the next limit stage. You're nervous, you consult the oracle, and it gives you a cofinal well-founded branch, and so forth. All right, so now we're going to focus down on a very special class of trees, and these are called strongly closed. So a tree is strongly closed if it's a +1 iteration tree. And in every model, every extender in the tree E alpha, its length is strongly inaccessible in the model where it's chosen from, and it's strong to its length. So these are very nice extenders. Okay? A strongly closed iteration tree is actually a plus theta iteration tree for all theta less than the least measurable cardinal of m. So +1, +2, they're all equivalent for strongly closed, for these kinds of trees. And that's why it didn't really matter. All right, so, whoops. Okay, now we're going to really narrow down and say it's a zero. Again, we have a coarse pre-mouse, and it's now a strongly closed iteration tree on the model. It's a zero strongly closed iteration tree if for all extenders in the tree, its length is less than the image of the critical point of the extender. That would be kappa E alpha star as computed in M alpha, okay, where this is the ultrapower embedding. So these are called short extenders, and their associated spaces are always the critical point. So these were the kind of extenders that were originally studied, iteration trees. Why the zero? Well, there's one strongly closed, two strongly closed. There's a whole hierarchy. But for the things we're interested in, by a recent result, the hierarchy collapses. All right, so I need to make one more definition. So we've now isolated on zero strongly closed iteration trees. We say the tree is weakly maximal. There's the definition. But let me give you the picture. It's weakly maximal if whenever you have a model in the tree that's tree related to another, so this is M alpha plus 1, this is M beta plus 1, then there's an extender that was used, that was E alpha, and then you got to this model by E beta, and if you look at these extenders, they have a critical point and an image of the critical point. Then the next extender's critical point has to be bigger than or equal to the image of the previous critical point. So this is called non-overlapping. As you move along a branch and you think of the extenders as arrows representing their strength, that are natural lengths or soups of generators, it looks like this. You're not allowed to do this and then do this. Okay? So along a branch, a weakly maximal iteration tree is a nice iteration. Looks like a nice iteration. A stronger notion, which is going to be the one relevant for the next few definitions, is when the tree is maximal. In a maximal iteration tree, all this is saying is that you have to choose alpha star as small as possible, subject to the rules of the tree. So weakly maximal does not imply maximal. Maximal implies weakly maximal, and that's a good exercise. So if you always go as far back in the tree as you can, you will generate a maximal tree. And that's equivalent. That's what a maximal tree is. So you're not allowed, you have to have courage The further back you go, the more likely you're going to get into trouble, because in some sense the further the extender you're using is from the model that you apply it to. Okay, so the further back you go, maybe even the ultrapowers aren't well founded. All right, so now the two central iteration hypotheses. If you have a coarse, suppose you have a countable coarse pre-mouse that elementarily embeds into a rank initial segment of V. Then there is an iteration strategy of order omega 1 plus 1 for zero closed maximal iteration trees on the mouse. So you choose a pre-mouse that you can embed into V, and you have an iteration strategy, an omega 1 plus 1 iteration strategy for that mouse, a pre-mouse. And then there's the weak unique branch hypothesis. It seems unrelated. Suppose you have a rank initial segment of V that's a coarse pre-mouse, and you have a countable zero strongly closed maximal iteration tree on the coarse pre-mouse. Then T has at most one cofinal well-founded branch. Okay, so we're restricting to zero strongly closed maximal trees in all of this, and it's a theorem of Martin and Steele that this implies this. And that theorem is true for a much more general class of trees. Okay, so those are the two central iteration hypotheses. These are open. And these are very powerful hypotheses. You can do a lot with them. But why the restriction? Well, nature is not kind. Here's a counterexample. Suppose there's a supercompact cardinal. Then there exists an extender E whose natural length is pretty short. It's at most 2 to the 2 to the kappa of the ultrapower, where kappa is the critical point. So that's not a strongly closed extender, but it is a short extender. Its space is its critical point. And then there's a zero strongly closed maximal iteration tree on the ultrapower of length omega, whose critical points are all above kappa E star, and T has two well-founded branches. So the weak unique branch hypothesis is false if you try to relax strongly closed in just one instance, the first extender used. Okay, so you have to restrict to zero strongly closed trees. Okay? So all that's happening here is you're applying one extender. First, oops, I gotta do the marker. You're applying one extender to get your new model, and it's not a very long extender. And then in V, we're just building a zero strongly closed tree on this as the initial model that has two well-founded branches. The whole thing is an iteration tree, but it's not a strongly closed iteration tree. So it doesn't refute the hypothesis. But it does say you've got to be careful about how you state these hypotheses. And then the other counterexample, same situation. We have this little tiny extender. We now have an iteration tree of length omega squared. It's zero strongly closed on this model. It has only one cofinal branch, and that branch is not well founded. So that's bad, right? You might be just merrily going along and encounter this tree, and you're stuck. Only one branch, and you can't choose it. So that's why.
What's the strength of the? You know what real is?
Oh, the strength of the is not is. You can actually vary this and get the strength anything you want, but you can't make it strongly closed. Okay. So the only reason I state these two things is that these show that you really don't want to weaken or alter the definition of the iteration hypotheses. And they also give some pause. If there is an outright proof of these iteration hypotheses, somehow strongly closed has to figure in the proof in a very strong way. Okay? All right. So back to the problem. Generalizing LMU. We want to try to generalize that. Well, one extender is not enough. One extender is good enough to generate very powerful embeddings, but you can't use it to build the model that we're looking for. And so this is an easy lemma. It follows from Cohen's analysis. Suppose E is an extender whose length is less than the image of the critical point, so kappa E star. Then L of E, which I guess I'm being precise here. That's what I mean by L of E. Remember, E was a sequence of ultrafilters, so technically L of E would be L. So I have to repackage E to get something. I want the smallest model, that the restriction of E to the models in the model, and that's what this gives. All right, so if you take one extender whose length is not too long, and you construct from it, you just get LU, where U is the normal measure on the critical point given by the extender. You don't get past what Cohen did. Even though this extender in V could yield a very strong embedding, when you construct from the extender, all the stuff you needed to verify the strength of that embedding disappears. Now, you could try to lengthen the extender, and this is a much more complicated lemma to prove. This follows from Cohen's analysis. Suppose you have an extender, and, well, here it is, F, and we take F and we restrict it to JF of psi for some ordinal less than the critical point, J of the critical point, such that the strength of F goes past the ordinal that I'm restricting to. So I'm choosing an ordinal less than the image of the critical point, then moving that by the embedding and cutting the extender there. Well, then L of E can transcend LU, one can show, but curiously in L of E there's no Woodin cardinal. In fact, there's no inner model of a Woodin cardinal. So you can't get very far into the large cardinal hierarchy constructing even from long extenders. Now you might quibble about why am I requiring that E be the restriction of this extender to something below its strength. If you relax this condition, then you can code anything up you want. You never want to take an extender whose length is, you always want to work below the strength of the extender when you construct. Otherwise, terrible things can happen. Okay, so those are two theorems that tell us that you can't use one extender. Whoops. So, if you can't use one extender, you use sequences of extenders, and these are the Martin-Steele extender sequences. So it's a doubly indexed family of extenders. So formally, the extender sequence is a subset of ORD cross ORD times V. If it's defined so that for all alpha, beta in the domain of the extender of the predicate, it's giving you an extender, and we call that E alpha beta, and it's giving you an extender of length alpha. I didn't write it down here, but it will always be true that if alpha beta is in the domain of the extender sequence, then alpha beta prime is in the domain for all beta prime less than beta. So the way to think of this is it's a double induction, or a doubly indexed family of extenders. The upper index is the length of the extender, and the lower index is where in the sequence of extenders of length alpha you are. Okay. Some notation. If we take alpha beta in the domain of the extender sequence, we can restrict the predicate to alpha beta. That means you just restrict it to all pairs lexicographically less than alpha beta in the obvious way. Okay, so we're going to construct from this sequence. Okay. Oh, but before I do that, let me introduce our target hypothesis. A cardinal is super strong if there's an elementary embedding J from V into M whose critical point is kappa, such that V of J of kappa is contained in M. So the strength of this extender is where the critical point goes. Well, at least where the critical point goes. Assuming the weak, that's why I talked about iteration trees, assuming the weak omega 1 plus 1 iteration hypothesis and the existence of a supercompact cardinal, Martin-Steele extender sequences yield a generalization of LU to the level of super strong, so I need to define these. So here's the formal definition. an extender sequence, this doubly indexed family, is a Martin-Steele extender sequence if for every alpha beta in the domain, the following conditions hold. So before I get into the details, whenever you going to construct from a sequence of objects and you are aiming for a canonical model, you got to make sure that you're not inadvertently coding information, like repeating an object. Because how many times you repeat it, it's going to code up stuff. So all of these conditions, and there are only 3, are designed to block the obvious ways the adversary could try to code information into the model. The adversary being nature. So the remarkable fact is that these are the only things you have to worry about. That's what Martin and Steele proved. But you need that iteration hypothesis. Okay, well, the first thing, you want to make sure that your extenders come from real extenders and in a proper way. So that's for the coherence condition. So remember, I'm describing the requirements for alpha beta being in the domain. This is an induction. So there has to be an extender F such that alpha, that's the length of our extender on the sequence, is less than the strength of F. I'm going to require that the strength of F be strongly inaccessible in Malo. That's so that I can take advantage of the iteration hypothesis the way that I formulated it. E alpha beta has to be the initial segment of F up to alpha. We're going to require this condition, that alpha be less than or equal to kappa F star. And now this is the important condition. This is the coherence condition. If you shift the whole extender sequence by the embedding and restrict it to alpha plus 1, 0, what you get is E restricted to alpha beta. So what F is doing is it's erasing alpha beta from the domain when you apply the embedding, but leaving everything below alpha beta in the domain. That's all this is saying. So on the J side, alpha beta is no longer in the domain. In fact, beta is the shortest, smallest thing which is not paired with alpha in the domain. Okay, so that's the coherence condition. Novelty, now we're blocking the adversary. If beta star is less than beta, and then alpha beta star is in the domain, okay, you're not allowed to skip, and E alpha beta star intersect what we have so far has to disagree with E alpha beta with respect to what we have so far. You're not allowed to repeat information. So if you're going to put E alpha beta on the sequence, you have to have distinguished it from all the extenders already on the sequence by sets that have already been constructed. Okay, that's what this is saying. Okay, it's blocking coding, the way you might code information into the model. But now there's a related condition called the initial segment condition. Suppose that you have an ordinal alpha star less than beta, where kappa is the critical point of this extender. Then there has to be a beta star such that alpha star beta star is already in the domain and such that you have agreement. So what this extender is doing is blocking putting E alpha beta restricted to alpha star on the sequence. You couldn't have put it on. Okay, so that's another way coding could have been inserted into the sequence. You could repeat stuff, or you could put a long extender on that you should have been able to put an initial segment on. And how you skip codes information. Okay, so that's what a Martin-Steele extender sequence. Now they actually work with something called a dottage. It's exactly the same, except that now for every doubly indexed family, now not of extenders, but of sets of extenders of length alpha, this is how you construct from a dottage. We define this predicate, which is basically intersecting all the extenders. Okay. I'm not going to use what this is, so I'm going to go a little quickly here since I see I'm already out of time. Okay, so again, if we have an alpha beta in the domain of the dottage, we'll let E upper alpha sub beta be the corresponding element of the dottage. That's a set of extenders of length alpha. And then we have a Martin-Steele dottage. It's exactly the same. Okay, so if you take anything in E alpha beta, we have coherence. It has to come from an extender that shifts the dottage, erasing alpha beta from the domain. Novelty, you couldn't have put an initial segment on. It disagrees with all the earlier extenders, sorry, and the initial segment condition. It's exactly the same, but now we have sets of extenders instead of extenders. Why do this? Because you can define a dottage, right? Whereas to define an extender sequence, you need to make some choices. So that's why they did it. All right, so, but if you move to a dottage, how do we know that things are working out when you construct from the dottage? And that's the notion that the dottage is good. So the dottage is good if you take any element, anything in the domain of the dottage, take any two extenders in that set, then those extenders agree on the inner model. So the extenders are not the same in V, but they have to agree in the model. And so we're getting an extender model. And then Martin-Steele showed that if you assume the weak omega 1 plus 1 iteration hypothesis and that E is a Martin-Steele dottage, of course they didn't call it a Martin-Steele dottage, then E is good. And they also showed that if you have the same iteration hypothesis, a supercompact cardinal, much less is needed, then there actually is a dottage such that there's a super strong cardinal in L of E. So you reach super strong. Now if you think about it, this goodness is like Kunin's theorem on the uniqueness of LU. The two objects are agreeing. So this really gives a generalization of Kunin's theorem for LMU or LU up to the level of super strong cardinals, but it needs this iteration hypothesis. But this is great. We're getting up to super strong. Now I'm just going to state a theorem. It'll be proved in the notes. There's an amusing generalization of the theorem about goodness that really shows you that things are just like the one measurable case. So here's the theorem. Same iteration hypothesis. Suppose you have two Martin-Steele dottages, but now let's just require that they have the same domain. Then the models you obtain are the same, and for everything in the domain and every extender, they agree. So the inner model given by a Martin-Steele dottage in V is uniquely defined by the domain of the dottage. That's just like LMU is uniquely determined by the associated kappa. So it's playing the role of kappa now as the domain of the dottage, which is just a bunch of pairs of ordinals. Okay, so this all looks really great. Looks like we're almost there. So now we want to go past, because we want to get to supercompact, so we have to allow long extenders whose length is bigger than the image of the critical point. So this now defines a generalized Martin-Steele extender sequence. They did not look at this. And it's the same conditions. Coherence. What I've done is drop the shortness condition, that's all. So same coherence, same novelty, and same initial segment condition. We are no longer requiring that the length of the extender be less than or equal to the associated image of the critical point. Okay, so this is how we would try to reach beyond super strong. Okay, so 20 minutes. Okay, now that's a lot of definitions. So now how about one more definition and then we prove a lemma. Fast club forcing. Here's the situation. We have a strongly inaccessible cardinal delta, and we want to add a fast club at delta by less than delta closed forcing. Fast just means you get inside every club eventually. So you just write down the obvious conditions. Conditions are pair C. C is a bounded closed subset of delta. X is a set of closed cofinal subsets of delta of cardinality less than delta. If you have two conditions, I realize here it's very controversial what the order should be, but I'm a rebel, so we'll say this condition is stronger if C is an initial segment of D, and the difference, so all the things above the maximum element of C, are in all of the closed sets that were mentioned here. So these are the constraints. This is an initial segment of our final fast club, and you have to stay inside all of these closed sets as you lengthen C. And it's easily checked that this is less than delta closed. If you have a generic for this, and you take the union of all the little closed sets that occur in a condition, then this is a closed cofinal subset of delta. And for all closed subsets of delta that are in the ground model, this generic club is eventually in that club. It's a fast club. Okay? Okay, here is the useful lemma. Suppose kappa is strongly inaccessible and A is a subset of kappa. Suppose we add a fast club at kappa, and in V of G there's a club contained in the generic club such that the initial segments of D are all in L of A for all gamma less than kappa. There's only one way this can happen. V kappa is contained in L of A. Okay, I'm not saying that the initial segments of CG are all in L of A, just that there's a club, cofinal in the generic club, all of whose initial segments are in L of A. So this is a necessary and sufficient condition. Obviously, if V kappa is contained in L of A, then, well, it's less than delta closed forcing, so you don't add any bounded sets. Okay, so this has a pretty easy proof. It's an interlace. So we fix a term for the club D. By the homogeneity of the forcing, you can easily check that it's homogeneous. We can suppose that one forces that all the initial segments of tau are in L of A, and that tau is clubbed in closed cofinal in the generic club. So we have this term and a condition that's forcing that things are working. What we're going to do is build two filters and interlace the interpretation of this term to code up any bounded subset of delta. And it's quite easy. So for every gamma less than kappa, we'll let D gamma be the set of conditions in the fast club forcing, so that gamma is less than sup C or max C if you prefer. Remember, little c's have a top element. For all alpha less than sup C, either C, this condition forces that alpha's in tau, or it forces alpha's not. Easily generate many of these conditions by the closure of the forcing. And we're also going to require that the things that you forced in are cofinal. Now I really mean sup C minus the top element here, typo. Okay? Only one so far that I've noticed. Then for each gamma less than kappa, D gamma is dense. That just follows from our assumptions. And if we have a decreasing sequence of conditions of length less than kappa, then we can just take this canonical condition to produce a condition in D gamma. Okay? So let D be the collection. We have got gamma many dense sets. We'll say a filter is D generic if it meets all of these dense sets. If F is a D generic filter, then we let D sub F be the interpretation of tau by F. This family of dense sets is designed so that if F is a D generic filter, the interpretation of tau has to be club in kappa. So that's the point of this observation. Okay, so here's the key claim, and then everything really follows quite easily for this. The claim is that there is a pair of D generic filters such that if you do the increasing enumeration of their intersection, that's got to be a club because they're each club, then for all alpha, alphas in B, if and only if the min of the A, well, there it is. This is I've been handed D, and I'm building these two filters. The claim is there are two filters which code D up in a very nice way. Okay. Well, if one can prove this claim, then we're done, because for all gamma less than kappa, if we take the initial segments of these clubs up to gamma, that's an L of A. So this implies that for all gamma less than kappa, B intersect gamma is an L of A. That's what we want to show. We're showing that for every subset of kappa, all of its initial segments are an L of A, which is equivalent to saying B kappa is included in L of A. So this is really the key claim. Suppose you take a condition in our fast club forcing, which is in our dense set or empty. Then for each eta less than kappa, for which the maximum of C0 is less than eta, you can find a stronger condition in our dense set such that you're below the given condition. Eta is less than the maximum of C1, so you're lengthening past eta, but you add no elements to C1 up to eta. So you can think of it as we have a condition. Well, I think that's clear. We have a condition. You give me an eta. I can lengthen this condition and get into my dense set, but add nothing in this window. Well, that's exactly what you want, because now I'm going to build my two generics and hand back and forth and make sure that things are getting disjoint intervals except at limit points. Okay, so one uses this to construct decreasing sequences of conditions. The upper index indicates the 2, such that for all alpha the following hold. If I take the first conditions on these sequences, they have empty intersection. If I take successor clubs on these sequences, their intersection is the intersection of the predecessor. These aren't clubs, sorry, these are closed sets. If alpha is bigger than 0 and alpha is a limit, then C at 0 alpha, well, it's got to be the union of all the smaller closed sets. Soup, same on the one side. The max of the two is the same if the limit, and etas and beta if and only if the minimum of the next well, there. Okay? And where alpha is omega times eta. So at a limit stage, we're coding into our pair whether eta is in B by the relative behavior of these clubs. Okay, that's an easy construction given that property. Now the two filters witness the claim. Why? Because the intersection of the two associated clubs are just the maximum elements of the little closed sets where alpha is a non-zero limit ordinal on either side. And then we've now interlaced and coded up B. Okay, so it's just, you're going back and forth. At a limit stage, you've arranged that the maximum elements of these two clubs are the same. Now you have complete freedom on how big to make the next ordinal. So you can make it go either way. That on the 0 side, the next ordinal is less than the next ordinal on the one side or the other way, and you make that choice depending on whether an associated ordinal is in B. Okay, so that's the proof. Okay, so now I'm out of time. Weakly sigma 2 definable sequences. I'm not really going to use this notion for what I'll be doing, but it's absolutely central. So, and it's an amusing notion. So, and I shouldn't have done it, but I have stuck with it. So a sequence of sets is weakly sigma 2 definable if there's a formula phi with the following properties. If you take any beta and then 3 ordinals, if we interpret, so this notation here means in V gamma, look at all of the things where V gamma thinks phi holds at A, so we're interpreting the class defined by phi in V gamma. So if that interpretation in V eta 1 restricted to beta is the same as that interpretation in the third stage restricted to beta, then it's equal in the intermediate stage. You can't loop without being constant. Okay? It's a little bit like RE, I suppose. Okay? So what are some examples? Oh, we'll say that an inner model, transitive class, is weakly sigma 2 definable if the associated sequence of rank initial segments is weakly sigma 2 definable. What are some examples? Well, if you have a transitive class which is sigma 2 definable, then n intersect the V alpha, that sequence is weakly sigma 2 definable. That's an easy exercise. If for every alpha you let T alpha be the sigma 2 theory of V with parameters from V alpha, then the sequence of those theories is weakly sigma 2 definable and not sigma 2 definable. The increasing enumeration of all supercompact cardinals is weakly sigma 2 definable. Okay, so if n is a transitive intermodel of ZFC, that's what we're going to be interested in, which is weakly sigma 2 definable, and I have a sigma 2 elementary substructure of V, then n super V delta denotes the union of the sequence as defined in V delta, where phi is a formula that witnesses that the apparent sequence is weakly sigma 2 definable. And it's easily checked this is well defined because V delta is a sigma 2 elementary substructure. So if we have a weakly sigma 2 definable transitive class, we can unambiguously interpret it in V delta for any delta which is a sigma 2 elementary substructure of V. Okay, a cardinal is a strong cardinal if for every lambda there's an elementary embedding from V into M with critical point kappa such that V lambda is included in N. If you have a strong cardinal and n is weakly sigma 2 definable, then n intersect V delta is n as computed in V delta. Okay? And there's a proof, which since I'm running out of time, I'll let you just quickly look at it. It's in the notes. It's easy. If you have a transitive class which is weakly sigma 2 definable and delta is an extendable cardinal, and this is a typo, it should have been a strong cardinal, and V delta is included in M, then V is equal to N. And that's another easy proof. Second misprint. All right, here's the main technical theorem. Suppose you have an extendable cardinal, then there's a class generic extension of V in which the following hold. V of G thinks V is equal to HOD, and we don't add any reals. There's an extendable cardinal. Here's the technical thing. If we have if we have an E contained in the ordinals and delta such that L of E is weakly sigma 2 definable, delta is strong, now define X to be the set of delta, X to be the set of kappa for which there's an embedding from V of G lambda plus 1 to V of G J of lambda plus 1 with crit J equal to kappa and J of kappa equal to delta, and lambda is the least strongly inaccessible above kappa, so it's some bunch of critical points, then there exists Y contained in X whose initial segments are an L of E for all psi less than delta, and such that it's cofinal. Then L of E is V of G. Okay, so what this is saying is no matter how we're building this magic model so that no matter how you define in a sigma 2 or weakly sigma 2 definable way an inner model which can compute the initial segments of it's there, then there's only one way to do it, and that's a V of G. Okay, so I have 5 minutes. Maybe I shouldn't do the proof. Let me define the forcing, and then you can check the notes to learn the proof, or work it out for yourself. So we're going to do a backward Easton forcing such that at stage alpha, if alpha is strongly inaccessible in malo in VP alpha, then we do a 2-step iteration. We first add a generic subset to alpha plus, that's B, and then we do the fast club forcing defined in this model with gamma equal to alpha. What?
What type of generic?
Just a generic Cohen. Yeah, sorry, Cohen, just with initial segments, the simplest forcing. Okay? What do I do if alpha is equal to beta plus 1 now, and beta is strongly inaccessible in malo. So at stage beta, I just did this. Then you do a one-step forcing to code up this information into the power set function before the next strongly inaccessible. The reason I added that generic set is to get everything to be a set of ordinals so that there's a canonical choice for this forcing and I don't need global choice. So it's a standard way of taking a set of ordinals and coding it into the power set function below the next strongly inaccessible, and all I want here is that the forcing is beta plus closed. Okay? That's the forcing, and at all other stages, p alpha plus 1 is p alpha. So I'm adding these fast clubs, and that's what's going to make everything work. Because I'm out of time, you're going to have to read the notes. So it's not a hard proof. And I'm sorry about this going through. I hate it when people do that. But I really thought I'd get through this stuff today. Okay, so here are the applications. Suppose V is equal to Hod and there's an extendable cardinal. This is an application of the proof, not of the theorem. Then you can build a generalized Martin-Steele extender sequence E such that E is sigma 2 definable. There's no issue here because V is Hod. For every alpha beta in the domain of E, alpha is at most the image of the critical point plus 1, and V is L of E. Well, that's not so good. That means it's not a canonical model. All right, so the response here would be, all right, you just need more conditions beyond novelty and the initial segment condition. Those were blocking two coding methods. There's obviously something else going on. We just need another condition. No, this is a corollary of the technical theorem. Assume there's an extendable cardinal, class generic extension. It's the same one. V of G thinks Hod. V is equal to Hod to have an extendable cardinal. Take any generalized Martin-Steele extender sequence, which is sigma 2 definable, and such that V of G is not L of E. Then for all alpha beta in the domain of the sequence, if kappa E alpha is a strong cardinal in the model, then alpha can't be any bigger than the image of the critical point plus 1. You can't put long extenders on the sequence. And this is any sigma 2 definition. So you can't revise the initial segment novelty condition by any sigma 2 condition. Otherwise you would violate this. Okay, and this is just an immediate corollary, and here's the argument. And I want to finish, and I have 2 minutes, so I'll just leave it for the notes, but it's an easy corollary. It's the coherence condition that's giving you the images, that set Y. All right. So suppose you have a generalized Martin-Steele extender sequence and something in its domain, and alpha is less than or equal to the image of the critical point plus 1 for E, where E is the L of E extender given by, this is a V extender, so that induces an L of E extender, then the strength of that extender within the model is at most the natural length, sup of generators of the model, and that's at most the image of the critical point. So there's no direct construction, direct generalization to LMU which can get beyond the level of super strong cardinals. That's what this is all saying. You cannot, that the Martin-Steele theory went as far as it can go. You cannot get past super strong. And then the coding you can't block is the image of the critical point. Once you start putting the forbidden information, if you want, is you're in the inner model and you see objects which come from extenders in V. And you better not be able to figure out the critical point and the image of the critical point for those extenders. And there's no way to block that information in the Martin-Steele methodology. We need something new. So that's good news is we can get to super strong. Bad news is to get past super strong, and I'm ignoring the iteration hypothesis now, we need a completely new methodology. Okay? So tomorrow, not tomorrow, yes, tomorrow. What day is today? Today's Monday, Tuesday, tomorrow. I'm going to go one level deeper. So we tried for the simplest way, generalize LMU. construct from a coherent sequence of extenders, see if we can get a model that approximates L, at least as far as the reals are concerned. Okay? And you can't do it. You can only get up to super strong. So there's something happening. So now the next level of models are the true fine structure models. These are called partial extender models, and we're going to now investigate those. And what I'm going to show tomorrow and then I guess Thursday is that there's a success. You can go a certain distance with the same iteration hypothesis, and then the whole methodology breaks again. Okay? So, and how far can you go? You can actually reach the finite levels of supercompactness. That looks great because, you know, there's clearly a difference between super strong and kappa plus supercompact. But boy, if you can get into the finite levels of supercompact, surely you're getting close to supercompact. And the answer is no, you are not. Okay, so that's what I'll be doing tomorrow and Thursday. And the notes have all the details, and as soon as I feel confident enough that I've only said 200 false things in the notes, I'll give them to Asaf and he'll post them. Beta version. So you all have to find misprints in the notes and give them to me. Okay, thank you.